All right, we're here to do chapter 12 examples, and I have 6 examples picked out this chapter that we're going to run through together. A couple of them are pretty short. And the first one, it references exercise 6, the problem before this in your text. So I've written down the 3 properties that we are wanting to prove are valid for ZP, where ZP is prime. So the 3 things we're going to try to prove is we're going to try to show that a squared equals a implies that a equals 0 or a equals 1. A b equals 0 implies that a equals 0 or b equals 0. And ab equals ac and a not equal to 0 implies that b equals c. So these are 3 properties that we want to try to show are valid for ZP, where p is prime. So, first off, something important to note over here. In ZP, we will have a multiplicative inverse for all a not equal to 0. So that is going to be kind of an important piece for us to use. We know that we have a multiplicative inverse based on our one example that we looked at where we talked about Zn and what items would have multiplicative inverses. We said it was going to be Un, and when n is p, everything that's less than p is relatively... Nope, I didn't have to sneeze. I thought I had to sneeze. Sorry, guys. See, I'm still weird. Even on video, I'm still weird, and you guys still love me. It's okay. Okay, focused. I am focused. So, we know that all of our units, things that are going to have multiplicative inverses, are elements of UP, and UP is going to be everything except for a equals 0. So, this is an important fact that we are going to use as we work through these proofs. So let's start with part A. We have a squared equals a. Let's let a be not equal to 0. So if a is not equal to 0, then what would we have? Because if a is equal to 0, this is pretty simple, cut and dry, right? If a equaled 0, then we would have 0 squared equals 0. Of course, that is true. So we're going to have a squared equals a. Let a not be equal to 0. Let's show that it has to then be 1. So, a squared equals a would imply that a inverse a squared equals a inverse a. We left multiplied by a inverse on both sides. This would give us a equaling 1. So a inverse a squared would be a, and a inverse a is 1. All right, so either a was 0, or if a is not equal to 0, it has to be 1. So we have our first property shown. Alrighty, B. So we're going to, without loss of generality, we're just going to say, without loss of generality, let a be not equal to 0. So, AB equals 0. Let's multiply on both sides by A inverse. So A inverse AB equals A inverse A. So AB equals 0 implies that, oh, I misspoke there. That's a 0. So A is not equal to 0, has a multiplicative inverse, and so let's left multiply on both sides by it, and we would have B equals 0, right? So if A is not equal to 0, then B is equal to 0. We could play the same game going the other way, saying, well, assume B is not equal to 0. We could then multiply on both sides by B inverse, and we'd get that A had to be equal to 0. So one or the other of them has to be equal to 0. C. Let's have AB equals AC. A does not equal 0. So this means that we could left multiply on both sides by A inverse, right? So we could have A inverse AB equals A inverse AC, which would give us B equals C. So we've got all of our properties shown. Our biggest thing was to note that as long as A is not equal to 0, as long as we're in ZP, then A has an inverse. That was our big key to use for all of these here. All right, we're going to look at number 19. Number 19 is going to define for us what the center of a ring is. So we're going to prove that the center of a ring is in fact a subring. So of course we need to have the same operation. We need the center to be a subset. And we need to show for AB in the center that A minus B and AB are in the center. Now, to be in the center, we have X that is in R, our ring, such that AX equals XA for all A in R. So, let's let AB be in the center. Then consider A minus B times X. Now let's play with our properties that we know. We know that this would be AX minus BX, right? Well, this is equal to XA minus XB because A and B are in the center. And this is equal to X times A minus B. So A minus B then has to be in the center because we showed that it commutes with X. Okay. Now let's consider AB times X. Well, that's A times BX, which is A times XB, which is AX times B, which is X A times B, which is X times AB. Which again, that shows that AB is in the center. So we've shown the things that we need to show in order to say that this is a subring. So we can say, therefore, by theorem, let's see, we used theorem 12.3. The center is a subring. Next, we're looking at number 31. And this is just a given example one. It says, give an example of ring elements A and B with properties that A, B equals 0, but BA does not equal 0. And when I see this right here, what I'm really thinking about first off is AB does not equal BA. So this is not commutative. When thinking about things being not commutative, we are often thinking about matrices. If I could spell matrices. I think I spelled that correctly. We'll just go with it. That's how you spell matrices now. So we want to think about matrices. Let's work in M2 with integer entries. Let's consider A, let's let it be 0, 1, 0, 0, and B, let's let that be 1, 0, 0, 0. So let's do AB real quick. What does AB equal to? So rows times columns, 0 times 1 plus 1 times 0 is 0. 0 times 0 plus 0 plus 0, that'd be 0, 0, 0. So this essentially is our 0 element. That's our additive identity. And let's look at BA. What is BA equal to? So row times column. We would have 0, 1, 0, 0. I think I just did that, and that is not equal to the 0 element. So AB equals 0, BA did not equal 0. So here's an example. All right, let's look at 32. Let n be an integer greater than 1 in a ring which x to the n equals x for all x. Show that AB equals 0 implies that BA has to equal 0. Well, if this is true, then BA has to equal BA all raised to the n, correct? Let's rewrite this. Let's write this as BA, BA, and then this is BA to the n minus 2. I'm going to specifically group there that we have an AB sitting there. Well, AB is 0, right? We have AB as 0, so that'd be B, 0, A, BA to n minus 2. That would have to equal 0, because anything times 0 is 0. That gives us BA equals 0, so we've done what we need to do. So again, a pretty quick, short proof. 33. Suppose that R is a ring such that x cubed equals x for all x in R. Prove that 6x equals 0 for all x in R. Okay. Well, what if I looked at, and I'm going to carefully choose my value to sub in for x. I'm going to look at, instead of x, 2x. 2x would have to equal 2x cubed, right? What is 2x cubed? That would be 2 cubed is 8 times x cubed. Well, x cubed is just x, right? So that's 8x. So now we have 2x equals 8x. How does that help us? Well, let's subtract 2x from both sides. And when we're thinking subtracting 2x from both sides, we're saying to ourselves, I'm going to add my additive inverse of 2x to both sides. It's really what we're doing. And we come up with 0 equals 6x. Now we used an element in general, so we're able to say that 6x equals 0 for all x in R. So this one, it was all about knowing the right, careful starting place in order to make this work. So sometimes you might have to play around a little bit to find that right thing. One last one, is Z6 a subring of Z12? So we need to say, is this a subset? Yes or no? Is it under the same operation? Yes or no? And if both of those are yes, then we'd show for A and B in Z6 that A minus B and AB also would be in Z6. Z6, yes, that is a subset of Z12. So you have Z6 is a subset of Z12. Are they under the same operation? Z6 is mod 6, Z12 is mod 12. So, not the same operation. Not the same operation. So Z6 is not a subring of Z12. All right, that wraps it up for examples from chapter 12. Again, if you have any questions, please do let me know. Shoot me an email. Make sure you're staying up with your homework, and